Too many struggles with them.
అంటే అందరికి సపరేట్ సపరేట్ ఇచ్చినావు అందరికి అందరికి
Shall we start, sir?
Yes, sir, I'm ready. Whenever you say.
Yeah, good morning to one and all. Welcome to the 2-week faculty development program on recent development of nanocomposites and smart materials in aerospace industry. So today's speaker, Dr. Prakash Jadhav, sir. Sir is a HOD and professor at the Department of Mechanical Engineering, SRM University, Amaravati. So I welcome you, sir, to take the session for AICT approved FTP. So today's session will be from 10 to 12 p.m. Okay, so sir will be handling 10 to 12 p.m.
Okay, thank you very much.
Welcome to the session.
Yes, sir.
Yes, yes, sir. You can you share the screen, sir?
Okay, I will share. Okay, I think you have to unshare, then I can share. You have to stop sharing. Okay, thank you.
I did, sir.
Okay, can you see my slides? Hello?
Yes, sir.
You are able to see my slide?
Yeah, yes, sir. We can able to see.
Okay. So all right. So I'm going to hello. Yes. So I'm going to talk about mostly the design of composite structures with respect to aerospace applications. Okay. So as part of this, hello. Hello. There is a disturbance, I think.
Sure,
Can you
sure,
mute
sir.
all?
I'll mute, sir.
Yeah. Okay. Thank you very much. So to continue this different topics under this design of composite structures for aerospace applications. Last time also I talked about some topics. This time I'm going to continue with some other topics. So there is one more topic under this category, that is failure criteria for composite blades with wavy edge in aerospace application. Okay, so let me explain what is this thing basically. Okay. So if we talk about stress concentration because of the presence of hole or notch in a plate, there's a lot of literature available for that. If you just
Nation.
start to Google, so there is different papers are available which talks about presence of a hole or notch in a plate. Okay. Also, many have tried to do some predictions or experimental stress concentration studies to find the effect of presence of notch or hole and how it affects the failure of the structure. So under the plane tension and compression loading. Okay. So also some people have developed the analytical formulas based on the size of the hole or notch under tension and compression loading. But as far as the this composite fan blade is concerned, now composite fan blade is basically used in the aircraft engine at the front side. So if you look at the fan blade, it's a giant fan blade, like almost more than 1 meter long, and it's made of composite, and it's irregular shaped in the sense that this is not a planar structure. So this is a wavy structure basically. It's along the length also it's curved, and along the width also it is curved. So it's not a plain structure. So you cannot apply those simple analytical formulas or theories of tension and compression in plane structures. So this is basically out of plane, unsymmetric bending, twisting, a lot of things are happening. So like this. So this is a blade here, okay. As you can see, it's core along the length and it's core along the width also. And one side is like there's a leading edge made of metal, and the remaining structure is all composite. And the other side is called a trailing edge. The side which is on the left side is called the leading edge, and the side which is on the right side is called trailing edge. Okay. So what is the proposal here is can we implement wavy shape on the trailing edge side? So why we have to do that? So if we implement instead of the like if you say the straight edge there on the right side, instead of that, suppose if we implement the wavy structure there, okay, wavy shape, so that will add to some aero efficiency benefit. Okay, so the aero efficiency benefit is like only like 0.1 to 0.2%. It's not high, but in terms of the aviation, it is very high because it can have cascading impact on the other things. So this 0.1, even 0.1, 0.2% efficiency benefit also is very high in terms of aviation. So if we implement those wavy shapes on the right hand side of the figure, that is the trailing edge, it's going to give some benefit. So how do you implement that? Okay. As you can see, the blade is not a planar structure. It is curvy both on length and width-wise. Okay, and then the design criteria for this blade is of course burst strike. So bird comes and hits on the leading edge, and under that burst strike loading, the blade is going to bend. Blade is going to bend lengthwise also and the widthwise also. So it's basically a bending problem. Okay. So then basically what we have decided is, can we create some kind of simplistic coupons which can mimic this blade bending behavior, and also we can implement those wavy shapes in that coupons and then test it and then come up with some kind of design criteria for those wavy shapes. So this is what the project is all about. So we'll see. Okay, so as you can see, what we did is we used finite element analysis to create these simplistic coupons, which can be tested in the lab, just like 10-inch long and 3-inch wide like this. So as you can see, the left-hand side figure, that is the baseline coupon, which is like straight. Okay, there are no wavy shapes there. Straight coupon, 10-inch long and 3-inch wide, and the other cases where we can see the wavy features are implemented on one of the edge of the coupon. Okay, just to find out the effect of that wavy feature. So there are different wavy features that we were playing around, almost 25 designs. So out of that, only 2 designs I'm showing up here. To basically come up with the criteria, we are using this few designs first. So as you can see, case 3 is like higher, like you can see the higher size wavy shapes are there, and the case 19 is like very small wavy shapes. Okay. So this we implemented on the one edge of the coupon, and then we did the API analysis, and based on this design, then we actually try to fabricate the coupons. As you can see, we fabricated the coupons, and then we took them to the lab, and we did this 4-point bending test. So why bending? Because as we have talked about earlier, under the burst strike load, the blade is going to bend lengthwise and widthwise also. So the similar kind of boundary condition we are trying to create here, like similar kind of loading condition that these coupons are being subjected to, they are bending. Okay. So under the bending, of course, you can see that the small wavy features are showing different response, and the bigger wavy faces are showing different response, because when you bend the blade with bigger wavy shapes, of course, the wavy shapes are not symmetrically bending. They are going up and down, and also the failure is happening differently. So we did put strain gauges on the, as you can see, exactly the bottom point of this wavy shape. There's one strain gauge. Here also there's another strain gauge. Here also there's another strain gauge, and then one strain gauge far away from the wavy face. Okay, like this. So similar strain gauge we put on both the coupons, and we ran the test. Strain gauges were used to measure strain level. So what does it give us? Okay. So as you can see, the maximum stress far field tension strain gauge is showing these readings. Then far field compression strain gauge, and then the scallop strain gauge. Scallop means the one wavy feature we are calling as one scallop, second wave feature, third wave feature, like 3 scallops, like 1, 2, 3, like this. So basically 3 scallops are there. So these are the strain levels, and the scallop strain in tension, scallop strain compression tension, in the sense that when you bend the coupon like this, of course the bottom side of the coupon will be under tension, and the top side will be under compression. So that's what it's showing here, the compression strain gauges and the tension strain gauges. So as you can see, the load is similar. But under the similar loading, the baseline coupons and the HTE coupons, that means sculpted trailing edge, that is the wavy feature coupons. Okay. So baseline coupons and wavy feature coupons. So these are the strain levels that can be seen. So as you can see, the wavy coupons are failing under low level of strain compared to the baseline strain. Here also, as you can see, and FEA strain levels also are shown here. Okay. So then FEA model. Hello. There's some disturbance. Yeah. So FEA model, as you can see, so we try to optimize the FEA model. Okay. So what we did is the half thickness of the FEA model. If you look at the thickness here, hello. So half thickness of the FEA model, if you look at it, the top half and bottom half, you just vary the modulus, the compression side modulus and tensile side modulus, and then try to match the results. That's just one way to match the experimental results with FEA. And that's what we did. And we found that the trial 4 is giving good results. So that's what we use for further calculations. Okay. Then, as you can see, the strain variation along the width for baseline and other cases are plotted in APA using the experimental failure load. And the characteristic distance is computed. So what is the distance basically? Characteristic distance. So as you can see here, where the baseline plot is meeting the other plot. So if you plot the strain variation, like tensile strain, how it is varying along the width. Strain, hello? Can you mute the participant? Whether I can mute it.
Gmail open.
Hello? Okay. So as you can see, yeah, so the tensile strain variation along the width and the compressive strain variation along the width. And if you look at the baseline plot, okay, so where the baseline plot is meeting this other plot, where the strains are very high near the scallop, and as you go away from the scallop, so what I'm trying to say here is, if you look at the scallop, if you plot the strain variation along this width, okay, so here at the bottommost point of the scallop, of course, it will be very high strain, and then as you go along the width, the strain level reduces. Okay, that's what happens. Similar things is happening here. As you can see, the strains are very high. Okay, so as you can see, when the baseline model meets this variation of the core, then we get some distance, characteristic distance. So what does it mean? Here. So if you look at the figure here, basically, so this is a coupon with a wavy feature, and there's a coupon with the without wavy feature, that's baseline. Okay, so the strain variation along the width for this wavy feature coupon and the baseline coupon. So there is some distance where if you measure the distance, there is some distance from this bottom point along the width to the inside part here. There is some characteristic distance at where the strain level comes down to the level which was there in baseline coupon. So that distance is called as characteristic distance. So we are trying to find that distance here in this analysis. Okay. So here, so that distance is like 0.25 or 0.62 like this. So the distance we are trying to find. Compression side different, tension side different like this. Case 3 and case 19. So based on the different variations of design, you are trying to find the distance. Okay. Is it 0.62 or 0.25 like millimeters? Okay. So the load prediction at different characteristic distances is computed and plotted. So that also we can do. If we have different characteristic distances, how can we predict the load? So failure loads can be predicted from the both the combination of experimental and the AP analysis. Similarly, for other kind of coupon ST17, there also we can predict the failure load at different characteristic distances using the AP and both experimental analysis. Okay, and the prediction versus the real load. Prediction values are very close to the real experimental failure load. Okay, that is observed here. So characteristic distance that I talked about. If we study like baseline coupon and the case 3 coupon and the case 19 and ST15 and ST17, these are just the different designs that we were working on. So for all these 4 designs, we compared with the baseline coupon, and we used the experimental results, and we also used the analysis results and found out this characteristic distance. And the characteristic distance looks like 0.4325 is the kind of average distance here that can be used for prediction of failure load for all the new cases. Okay, that means what we are trying to do here is the thing is why this project is on basically. So I'll tell you the background again. Now, if you decide to implement this wavy features on this trailing edge of the blade, of course, you cannot manufacture the blade with, let's say, 25 designs of the wavy feature, because manufacturing the blade with those 25 designs and testing them is going to take like huge efforts and cost and too many complications. Okay, that is why we are trying to analyze, trying to get develop a technique using the coupon level testing analysis. Okay, all this coupon level testing analysis, so that we can actually evaluate all these different designs on coupon level itself and find out which design is better, and then move to the blade. Okay, that's what the purpose of this thing. Okay, so that's what, once we find this characteristic distance at which the strain variation meets the baseline level, so that can be used to predict the failure load for new cases like this. So as you can see, the 0.435 distance can be used to predict the failure load of new specimens. Okay, and no need to make the new coupons and test it experimentally. That is what the basic purpose of this particular analysis and this thing. So conclusion, this is a new methodology that was proposed here to predict the failure load of new wavy edge specimens. So how do you predict the failure load? Because once we know the strain level, like for any new coupons, you can measure the, you can actually use the characteristic distance and predict the strain level. From the strain, you can failure strain. From the failure strain, you can find the failure load. Okay, so that's how you predict the failure load. So this methodology is proposed here to predict the failure load of new wavy edge designs in the trailing edge. Coupon-based approach is used. Characteristic distance is found by some initial testing of coupons. By some initial testing of coupons. So further testing of new cases of blade designs are not required. Directly, failure load can be predicted for new designs using API modeling. Okay. So this is what the conclusion of this work. So I have one more topic here. So let's talk about that. Okay, so this is another topic, So it talks about this indentation. So you must be aware what is indentation. So indentation, like you use some kind of metal indenter with a conical shape edge, and you indent any material. Okay, indent means like basically you take kind of a simple test system, and you kind of press that indenter along any surface. Okay, and then it creates some impression there. Okay, and you can actually measure the load and displacement while the indentation process is on. Okay, so how can we use this simple indentation experiment to measure the in-plane residual stresses in the aerospace structures? So where does this residual stresses happens in aerospace structures? So if you look at the aircraft engine, okay, so there are a lot of components inside the engine, like blades. Okay, not the composite blade I'm talking about. Now here I'm talking about the actual turbine blades. Okay, the composite fan blade is at the front of the engine, so it does not get subjected to high temperatures. Okay, that's why they use the composite there. But if you look at the turbines, like inside the aircraft engine, if you look at the turbine blades, all the turbine blades are made of titanium alloys, and they are subjected to very, very high temperature due to that combustion happening there and all that stuff. Okay, so for those kind of blades, generally they are coated with very high, what do you say, some kind of special coatings, which protects the blades from the very high temperature there. Okay, high temperature resistance coatings. Okay, so those kind of coatings are called as the thermal barrier coatings. Okay, so the thermal barrier coatings are used to protect the blades. So this particular my indentation experiments, what it will do, that on those blade surfaces, because of thermal barrier coatings and the below part, that is bulk material, there is some thermal mismatch is always created when it is subjected to very high temperature. And due to the thermal mismatch, there is some kind of residual stresses are always there. So how do you measure these in-plane residual stresses on those kind of coated components? So we have devised this technique, indentation technique, and we have tried to analyze the effect of this residual stresses. So this is what the project is about. Yeah. So What is residual motivation? Give the background that residual stresses affect the structural integrity and reliability. And indentation testing, of course, is a simple and most effective way to measure the elastic properties of bulk material. So what exactly we do? We do the study the effect of variable biaxial in-plane residual stress field on the indentation elastic properties. So how do you create this biaxial field? That also we'll see. Application of course thermal barrier coatings, residual stresses due to thermal mismatch, and experiment design considerations. So while performing this kind of experiments, we also analyze the other components like what are the different parameters those are affecting this uh, experiments basically. So error estimation and removal, those things also we studied. So let's talk about it. Yeah. So what is indentation technique? Okay. So there is a scientist called Oliver and other scientists called Parr, and they have developed these equations. Okay. So what is the equation means here? So if you look at this indentation plot, sectional plot here, okay, you can see that indenter is coming from the top. So you can see the indenter is coming from the top, and it is creating that impression there, like a valley. It's creating a valley here. Okay, it's creating a valley here. So these are the this is the nomenclature of that valley. When the indenter is putting pressure on the surface, it creates a valley like this. If it's a conical indenter, it is creating a conical valley like this. Okay. So basically, if you measure the this particular event when it's happening, indentation. So if you measure the load and displacement, okay, of that indenter, how the indenter is moving and how the load is getting varied there. So this is how it shows. So basically, you press the indenter against the surface, it goes down. Okay, it reaches the maximum whatever there, and then it comes back. Generally, loading and unloading. Okay, you load the indenter and it goes up to some depth and then comes back unloading. So if you perform this test, loading and unloading, so this is how we are going to get this plot. Okay, loading and unloading. So load versus displacement. So as you can see, there's a loading curve. Okay, it reaches to the top, and when unloading starts, of course, it is not going to follow the same path here because, of course, the metal is getting indented and metal is getting displaced. So of course, it is beyond elastic. So there is some plastic thing happening there. Okay, plastic flow is happening. That's why, as you can see, the unloading curve is different than loading curve. So this is what they'll follow unloading curve. And then from the unloading curve, they are using this equation to get certain characteristics of the material. Okay, so this maximum load is P max, and the slope of the unloading curve, okay, that is called S. Okay, so as you can see, you can use this equation using P max and S. What you can calculate? If you know the S, you can calculate the modulus of the material, and if you know P max, you can calculate the hardness. So there are certain equations which can give you this modulus and hardness of the material from a simple indentation test. Okay, then can we use this for our purpose? So that's what this project is about. So let's see. So some simulation, FEA simulation studies were done in literature, okay, and they have to try to find the effect of this residual stress changes in the residual stress on the stiffness and hardness of the material. So this is just one example where it shows what they did is they use different yield strength materials, like varying from a large range, like very low yield strength to medium yield strength to high yield strength, like different yield strength materials they use. And for those different materials, they tested this and found out that, I mean, artificially, they applied the residual, created the residual stresses in the AP model, and then they did some indentation in the AP model, and they saw the effect of this, like how the stiffness varies as the residual stress varies, and also how the hardness varies as the residual stress varies. Okay. The conclusion from this analysis, literature is like hardness and stiffness vary with the residue stresses. Plastic pileup and indentation work also found to be sensitive to level of residue stresses, and experimental validation is required. So this is the motivation basically. So all this analysis work, there was no experimental validation. So we went ahead and did some experimentation on this. So this is how it looks like. So there's an MTS machine. Okay. So what we did is designing this picture took long time. So as you can see, there's a special picture. Okay, it is mounted on that. There's a load cell coming from the top. Okay, and the load cell is attached to the indenter. There's an indenter there, and the indenter is going to indent on a specially designed specimen there. Okay, so this specimen is fixed in a picture. So if you look at this picture, this is a very special picture. Like you can see, the specimen can be clamped in 4 directions like that. Okay, with mouse, yeah, here. So as you can see, specimen clamping on left side, specimen clamping on right side, specimen clamping on this side, specimen clamping on that side. It is clamped, and then if you rotate the screws here, there's a bigger screw given here. Okay, if you rotate one end of the specimen will be clamped, other end of the specimen you can apply the. If you turn the screw in a clockwise direction, it will apply the compressive load on this side, and if you apply this screw on clockwise direction, it will apply compressive load on this y direction. Okay. Similarly, if you turn the screw on anti-clockwise direction, you can actually pull the specimen and apply tensile load here. Similarly, on this side also, if you apply anti-clockwise, then it will apply the tensile load. Okay, so this is a specially designed picture. So it was specially designed and created for this purpose to apply the biaxial loading. Okay. And so what we did is that like every rotation of the screw, like quarter rotation of the screw, will be calibrated to some kind of loading. Okay, so every quarter rotation of the screw will apply some step of the loading like this, and this loading can be. I mean, what we did is we put the strain gauge on the specimen, and accordingly we measure the loads. Okay, whether it's a tensile or compressive, whatever stresses are there, we measured. So indentation, basically the indenter was a Rockwell type conical indenter with diamond tip. Okay. So initially what we did is we did some AP analysis on the specimen, and then designed the specimen like this octagonal shape specimen with all these holes for the clamping like this. So it was designed in APA, and then we manufacture the specimens for different materials. Okay. So where we should place the strain gauges, that location also we found, so that it should not be near to these holes, because if you look at near the hole, there's a stress concentration here. The specimen should be placed somewhere in the middle part here, where there is uniform strain distribution is there. So as you can see, there are different specimens are there. In the aluminum, we use the different grades like 1100, 50, 52, 60, 61, 70, 75, polycarbonate and nylon, like different specimens we have used. All these different materials indicate the different stiffness and hardness and yield strength levels. Okay, different material means different stiffness, different hardness, and different yield strength levels. Because just to collect the data and then come up with methodology. Okay, approximate size of the specimens was like 72 by 3 millimeter. Okay. So as you can see now, the picture is very clearly shown. I can explain this here. See, actually, this whole top part can slide over this bottom part. Okay, so that you can adjust the where you want to indent, that you can adjust. Okay, location of the indentation can be adjusted like this. It can slide on this. Okay, and see, one side of the specimen is fixed here. This one side also is fixed. Other side here you can apply tension or compression load, and this side also you can apply tension or compression load. So x-axis you can apply tension or compression. Y-axis you can apply tension or compression, or you can have like different combination like tension X, tension Y, or tension X, compression Y, or whatever it is, like this. Different combinations you can apply. Combination loading, biaxial loading. Okay. So there were some errors that we found. Okay. So these errors like when you do the loading and unloading plot, okay, and you test it and you get a loading and unloading plot, and then you try to estimate the modulus and hardness from those unloading curve. So we found that there are errors in their value. So this is like if the modulus is coming as like overestimation. Okay. So suppose modulus of the aluminum is supposed to be 70 and we are getting like maybe 90, 100, 150, then what is the reason? So these are the errors that we found. Effective indenter shape, so there is one geometrical parameter. So parameter ranges from 0.72 to 0.79. So depending upon that, what we should use. The parameter, if you see here in the equation, the parameter will be there. Here, the parameter is there. Okay. So the parameter has a value and it affects the calculation. Then pile up errors. Pile up errors means yeah, like this, pile up errors. So as you can see, when you indent the specimen, okay, the conical indenter is coming down like this, and what you see is sometimes the material goes down like this when you indent it, and then when you pull it back, okay, unloading. When you unload it, the material again goes up like this. First the material goes down, then the material goes up. So it's called, if it goes down, then it's called sinking. If it goes up, then it's called the pile up. Okay. So if that thing is happening, then it shows a lot of errors. Okay. So these errors has to be estimated properly, and then we have to come up with an approach to adjust for those errors. Okay. So sometimes it can overshoot. Models can overshoot by 50% because of pile up errors. Okay, it's common for cold work soft metals like large E over sigma Y. It can be corrected. Okay. Then correction factor beta, that also varies from this range, so it can be adjusted, and then corrections can be done depending upon the shape of indenter, up to 10% of error in modulus. Okay. Thermal drift, there is change in dimension due to thermal expansion or contraction and creep. Okay. So some materials are sensitive to this. When they are loaded, they generate some heat and thermal drift that happens. Okay. So these are the errors shown here, like uncorrected and corrected because of thermal drift, or sinking and plastic, elastic plastic pile up, all these things. These are the errors which are seen and which can be corrected. Then as we talked about, like overestimation, sometimes it is underestimation. So the modulus is underestimated in the sense that the modulus could be like the correct value is supposed 70 GPa, but sometimes it is coming as 40 GPa or 30 GPa or 20 GPa, like the underestimation. So what could be the errors for underestimation? So machine compliance, that is loading frame. The loading frame has certain compliance, okay, and something getting lost in that compliance. So it can be removed by use of stiffer components, but of course it's not possible every time. But if you can come up with some statistical correction equation, then you can use that and correct for this load frame compliance. Plate bending effect for thin specimen. If the specimen is very thin and it is supported on two edges, then sometimes the specimen may bend slightly. And then specimen is not supposed to bend while doing indentation. Okay, specimen should be rigid, and the indentation should happen very smoothly. The specimen should not bend. So this bending effect also causes some underestimation of the modulus. Then surface roughness, of course, if you are doing nano indentation, like micro indentation is fine, okay, like millimeters. But if you are doing nano indentation in nanometer level, those kind of indentation, of course, surface roughness matters a lot in those kind of things, particularly for spherical indenters, and you are doing nano indentation, the surface roughness matters a lot. Sinking errors and piling errors that we already talked about it. Sinking errors are common for low modulus materials. Tip rounding, error in hardness, very thin films. Then residual stresses. Okay, these are all these reasons for underestimation of modulus. Okay, so what we did is for studying the load frame compliance, what we did is suppose we attach this indenter in a different way to the indenter holder, as you can see. So this is a load spec actually, and this is indenter. Okay, so this is one type of setup. Like there is a steel holder there. From steel holder, there is another this sleeve, and then this sleeve is connected to the load cell, and load cell connected to indenter. Then we try to use this aluminum sleeve here. Instead of that, here is a steel sleeve is used, and here the complete setup is different here, as you can see. Like this, different kind of setups are used, and we saw that it is affecting this loading unloading cores, as you can see, and that's why it is affecting the modulus level, as you can see. It's affecting the modulus level. Okay, so this shows that the load frame compliance has a big effect on this testing setup. Okay. Also, effect of changing depth on the Indonesian modulus. So if you do the testing with different depths, then of course it is also shows the modulus variation. Okay. Okay. So possible questions for this load frame compliance and everything. So use of the load versus stiffness squared parameter. So this Oliver Parr, they suggested this use of this parameter, load versus stiffness squared, is equal to this values here, hardness, modulus, and all beta, and all these factors. You know. So if you use this directly measurable experimental parameter, okay, load versus stiffness square. So this parameter is independent of penetration depth and contact area, but it is available pile up and sink in errors and surface roughness. So because of this, this characteristics of this parameter POS square, that it is independent of many things, like many variations. It doesn't care about depth, it doesn't care about area, it doesn't care about pile of sinking errors, it doesn't care about surface roughness. So you can use this to adjust the compliance. Okay, if hardness is known, modulus can be calculated and vice versa. Okay, so for aluminum specimens, as you can see, the variations of this modulus, as you can see, when you load the aluminum specimen, like you load up to some extent, then unload it, then again reload it, then unload it, then again reload it, then again unload it, and reload it, like this. You keep on doing like this, you get a plot like this. Okay. Now, as we have seen earlier, that this unloading part of this core, that is can be used for calculating modulus. So if you calculate the modulus now at different stages, you see the modulus is different. Okay. 17, 18, 26, 38, and then 59. So at different stages, different moduluses you are getting. Okay. So this is what is happening. Also the bending effect, like if you have a specimen like this, okay, and specimen thin, suppose, then you are applying the indentation. So it may bend. So all those things are also there. So to come up with a methodology for removing this load frame compliance, as you can see, the load frame has a certain kind of stiffness characteristics, and so this is the equation here which use the load frame compliance. C is the total compliance, and CT is the load frame compliance. Okay, and if you plot them against these parameters, like total compliance versus this A value here, if you plot it, and that P over S square, that parameter that which is used for getting the correct value. So if you use P over S square and plot it against indentation depth, so correct load frame compliance is the one which produces the flat core of P over S square. Okay, if you look at this bottom core here, okay, look at the bottom core here, and that is almost flat. The bottom core is almost flat here. Okay, so this core will give you the P over S square, correct P over S square value. Okay, which produces the flat core. So this core has a load frame compliance of 0.25 times the load frame compliance. So that this one you correlate here and then get the compliance of this load frame, and then you do the adjustment. That's how you do this. Okay. you adjust for the load frame compliance accordingly. So coming to the final calculations here. So as you can see here, the hardness and the stiffness basically. Okay. So when you vary the residual stresses, here, as you can see, the 0 is the no residual stress, and right side is the tensile residual stress. Okay, and the left side is the compressive residual stress. So as you can vary from the compressive residual stress of 0.6 to the these values are up to normalized. That's why it's looking like this normalized value. So let's say the compressive residual stress of 0.6 level to the positive 0.6 level, from compressive to the tensile. Okay. So as you vary the residual stress from highest compressive level to the highest tensile level, what happens to the hardness? Okay. So that's what is showing here. So this is the experimental result actually. Okay. This is the experimental result. Okay. And the experimental result shows that as your residual stresses in the material varies, but again you see the some plots are going from left side to right side and increasing. However, the other plots are going down, decreasing. So that depends on the material. Okay, that depends on the different materials. So as you can see, which one are going down, which the softer materials are different, the harder materials are different. Okay, so it depends on that. Which one is what? The softer materials are giving different response, harder materials are giving different response, like this. Okay, this is what shows like the hardness varies along the residual stress. Okay, stiffness also varies, like you can see here for the polycarbonate and the nylon. Okay, the response is different as the residual stress varies in the material. For the softer material like polycarbonate and nylon, the stiffness is going up. Okay, but for other materials, stiffness is almost constant, not very much. For some material, it is still increasing like this. So what is the use of all these studies that basically we are doing? So now we have these charts ready. Suppose the thing is, I am generating a data set basically. I'm using different materials of different yield strength and different modulus, and then I'm generating a huge data set. Okay, then I'm coming up with these plots. Okay, and then next time, let's say I get some random material for testing. Okay, I take it and then I test it, and then I can actually tell what is the stiffness and hardness. Uh, if I know the stiffness and hardness of that material, which I'll get from the indentation test. Okay, from indentation test, I will generate the stiffness hardness, and from that I can correlate to the residual stresses that are existence in that material. This is what the meaning of all this research. So basically, generating all the data sets. Okay. Generating all the data sets. That's what is. Okay. That's what. So the conclusion of this research is, so basically residual stresses seem to have a large effect on the indentation behavior of bulk material. Over and underestimation of the errors can be removed by a proper design of experiments. And this simple indentation technique can be used as a tool for identifying the level of residual stresses in thermal barrier coatings. So sometimes this actually it is causing some very small damage to the surface, but it's insignificant. Like if you use like nano level indentation, it's actually very small, the damage to the surface. So actually sometimes it is called non-destructive evaluation also, because I mean you can just by simple very small indentation you can find out what is the residual stress in thermal barrier coating. So it's a very nice technique, so it can be used. So it doesn't damage the material much, and you can immediately find out the residual stress. This is what the conclusion of this research. I think that is what I have today. Any questions? Yes, any questions? Hello. Do you have any questions? Hello. Hello.
Hello.
Yeah, so do you have any questions?
Participants, if you have any questions. Sir, I think no questions. So,
Okay, madam. Then thank you. Then that's it for today.
okay. So, can we close the session, sir, then?
Yes, ma'am. Okay. Thank you, madam.
So any questions with the participants, they can kindly pose the questions, or we have reached the end of the session. So thank you very much, sir. For this
Okay. Thank you, madam. Okay.
session. Actually, most of us are